will be more like you will need phase space scorers, something in the form of cylindrical shapes, not in just one single plane. So maybe what you if you will be dividing your simulation into several parts, then the good option will be to use a cylinder as a surface scoring option. Like here it says there is a cylinder possibility, and then you can explore this part, and this way it will allow you to divide your simulation into two steps. Like first score uh, a phase space outside your source, and then place your source in different location, and then do the second level calculation. So it maybe you can use that strategy, but I'm not saying that you should use it. Maybe you're interested, so I just shared my thoughts. Yeah, and it like I said before, the phase space scorer includes information on x position, y position, z position, direction, cosines, energy, weight, particle ID. Like I showed before, each particle is given a specific ID. So here it contains the particle ID, and then there is like you can flag if there is a third direction, cosine is negative, and yep. And you can score in two formats, like you can score in ASCII format or binary format. So that's it. Yeah, here are the IDs for the particles, like 22 is for photon, 11 is for electron, minus 11 is for positron, so on. Okay. Yeah, now the last part is you can filter your scorers as well. So by filtering, I mean, whether you just want to calculate the dose from, only include particles of generation, primary particles, not the secondary particles. So you can do it. You can select by charge whether you want to compute those from, or the any specific quantity from the positively charged particles, negatively charged particle, or neutrally charged particles. And you can similarly filter by mass, filter by kinetic energy, initial momentum, initial filter by kinetic energy or its ancestors when it's hitting the scoring component. Momentum, similarly here also its ancestors with like the secondary particles or and the primary particle hitting the scoring component. So there are like a lot of filtering options you have, uh, and like filter by process that is created. So whether you are just interested in simulating the impact of Bremsstrahlung, you can do it, or like you can score for two specific particle instead of one, like proton and neutron. So you can do it only one particle. So you can do it by specifying just one single particle and you call it neutron. And you can also filter by the origin of the particle. So like here they are including particles only from the jaws particle, not from the jaw component. So there are several options for you that you can use. And then yeah, so you can check all of these, and let me know in our next discussion if you have any doubt with any of these filters. Maybe you won't need them right now, but in your like advanced simulation you will be using some of these filters, and they are very useful. I use them frequently for my work. Sometimes I just want to simulate the dose and the phantom, and I'm not interested in anything that goes outside it. So I just use these filters, and sometimes if I'm interested in just photon fluence, so I just score for photons. I don't care about the electron and other things. So maybe uh, you will also need these one days. You can, like I said, you can include specify the RT structure like right lung and left lung, and then you can directly get the dose deposited, particularly in those organs. And yeah. Okay, and you can specify what kind of output you want. So there is a one program that is called root. It's actually uh, you can say data analysis tool. It is root CERN. Uh, why it's not following? Yeah. So it's a CERN root. It's another kind of like a data analysis tool that a lot of scientists when use when they have to do some kind of like heavy computing, and it is generally based on C++. plus plus. It is actually based on C++, plus plus, and you have to write a basic C++ plus plus code to analyze your data. You can plot a graph and do many powerful things with it. It is mostly used when there you have a very heavy data, or yes, very huge database, and you want to access things very fast. So root is very a good tool to use it. And then you can have XML files, like you can get output in Excel sheets. And then there is a DICOM file. You can get your output in DICOM file format, and other options is directly producing DVH, so you can do that as well. So for your outputting your scores, you have to output specify the name of the file, and then where you want to output it. uh, so that's it. And like I said, the output formats, you can define CSV, which is a type of Excel file format or text file format. Then you can define binary, root, DICOM, XML, and these binary 3D data outputs you can read uh, division just from the scoring water phantom or patient table shows the corresponding. Okay, so it there are like different uh, tools they're using, which you can uh, check the dose distribution. So there is like ImageJ, ParaView, Amide, and NumPy, and so it basically defines like how the dimensions are interrelated, like x, y, z axis, like x-axis of topaz as width for ImageJ, and x for x-axis for the ParaView. So you can check it if you want to use any of these tools. So you can use we will in this uh, workshop, in the last part of our workshop, we'll be using NumPy to uh, analyze your data, whatever output you get from the presence this simulation setup. We will be uh, reviewing or analyzing it using the NumPy. Okay, and yeah. So here is about the DICOM output. It is handled by a package that is called GDCM, which is pre-built into Topaz. And you have like two options. One is 16-bit by default if you don't specify, And if you specify 32-bit will provide you more information, more accurate. So I generally use 32-bit to specify my output type, using if I'm using uh, DICOM format as a output option for my simulations. And like I said, you can do a histogram output in the form of root or Excel file. You can define the bins in which you want to divide your output, and then like the limit, minimum and maximum. And yeah, similarly, you can output your DVH. You have to report what type of similar DVH you want to report, and then you can, or either you can do three output at the same time, like you want to calculate the sum dose deposited, mean dose deposited, and the cumulative histogram. So you can do it. Yeah. And now you can like let's say if you have a box and you want to have a variable voxel size along x, y and z, so you can define the number of bins x, y, z. And if similarly for cylinders, uh, you can divide it in r, phi and z. And for sphere you can divide it into r, phi and theta. And then you can bin by energy, like if you define 10 energy bins and you specify the energy, minimum energy and maximum energy that you want to score in that score, using that score. So yeah, you can bin by energy. But since we are not using the time, we won't be visiting the time feature of Topaz in this workshop. So for now, we skip it. But yeah, if you need help, we can discuss on this later. It's all about yeah, and then is like statistical information. So sometimes the information, or the uh, statistical uncertainties related to your calculations, you should know about them. And what is the percentage of uncertainty in your simulation. So higher the number of particles you simulate, 1 billion for brachytherapy simulations, and for high energy particles or MV beams, you need generally less than 1 billion, but you have to use some variance reduction techniques to make your simulations fast. And they also do like balance for the uh, take into account this low number of particles simulated. And maybe you are interested in scoring the sum of the dose, mean of the dose. So you can check, and you can use, like you can calculate the variance or standard deviation in your calculated uh, dose deposition or the fluence or any other quantity you score. And you can change the color component based on the scoring. So you can color by sum, so you can specify the color in your output. So yeah, it's you can these are generally you can restore the file, or you start every time with the new. So it's just simple. Okay, so we went through